day. My name is Mike Meekin, and today we're going to talk about technical scope management as it relates to the execution of a project. We're first going to examine a simple model that helps to visualize and communicate what is meant by scope, and we'll step through that model showing various ways in which discrepancy can occur within that scope as you proceed through the execution of a program. After we've identified these areas of discrepancy, we will then walk through how systems engineering in general and model-based systems engineering in particular can help to manage, minimize, and hopefully even eliminate some or all of these areas of scope. So first we start with customer expectations. This is a grand set of preconceptions on the part of the customer. It usually is not a consistent and coherent set, meaning that each customer or each person from the customer will actually have a different set. So there's some superset of expectations that the customer in general is expecting. From there, we then end up with a defined capability. This is typically what has been communicated as requirements for the program. So this is the contractual scope, the technical scope within the contract. So it's the technical contractual scope, and it typically has some level of disconnect with at least some of the elements of a customer's specific expectations. Ideally it wouldn't, but in reality it typically does. From that defined capability, the team now progresses through and starts to implement in a variety of steps and manners. There is also quite typically some sort of disconnect between what has been defined in the contract and what actually gets implemented. And this usually comes down to ambiguity in those sets of requirements, in which case, again, there's a discrepancy between what the implementer reads and what the actual person drafting those requirements intended. In addition, however, sometimes development teams will actually go above and beyond. This is typically a well-intentioned exercise, but they will define some capabilities that are in fact outside of the scope that has been defined in the contract. This becomes problematic, as we'll see a little bit later on here. Once the development team has finished their development, they then pass it over to the test team. The test team, in turn, now tests the scope. So typically, how they've defined the scope to be tested may have some sort of disconnect here between what was actually intended or what was actually developed and what was tested. It will always have the disconnect here because the test team has been working from the requirements, and these actually fall outside the requirements. So that gold plating, one of the problems with it is that those features or abilities or capabilities that have been added in pretty much never get tested in a formal manner, and therefore they never get evaluated. There's no assessment as to whether or not they are safe or introducing an instability or an insecurity in the system. And this is part of the reason that gold plating is not actually a good thing, although it is, as I said, typically well-intentioned. From the test, we obviously then have a set that is tested and passed, and we'll have a set that is tested and not passed. So from the original scope we had, from the customer's expectations, through the contractual technical scope, through to the actual implemented and developed scope, through to the tested scope, and then the tested and passed scope, we have these various areas of potential discrepancy. And what we want to do is we want to determine how do we identify those regions of disconnect, and how do we minimize the likelihood of their occurrence, how do we minimize the impact of their occurrence when it happens, and also assess the impact of that occurrence. So let's start going backwards. Tested and passed scope. This is easily identified. It's readily available from the test report. It's known as the maturity of the delivery. So what that means is we know that this capability is both present and functioning correctly because it's been implemented and we've tested it and it passed. Then we have the tested but not passed. It's also readily available from the test report. This is a set of known deficiencies in the delivery. Because they're known, that means that they can be assessed and evaluated, and they can determine whether or not the impact is sufficient that the build is still acceptable, or whether or not we really have to go in and fix these. The excess scope. this is one of the key areas of concern, of course. This results from a disconnect between a product baseline, final, and the product baseline, initial. So in systems engineering, the product baseline initial is what has been handed in to each individual team as their set of requirements that they have to meet. The product baseline final is fundamentally what the development team from each one of those teams has delivered. And this represents the discrepancy. And in many cases, as I said many times, this is actually a team that's actually trying to give a little bit more. They've seen an opportunity and they've said, okay, hey, we can add this capability as well. The problem is it hasn't been coordinated through the design authority to make sure that it aligns with all the other development teams that will later be integrating their products. And in addition, it's not tested because the test team doesn't even know it exists. So at best, it might get some testing and ad hoc testing when a tester simply sits down and starts pushing buttons and going through the keyboard. But it won't actually be assessed properly because you don't know what the what the acceptable results are from that kind of ad hoc testing, other than that you don't want it to crash. And the tester doesn't know exactly what it's supposed to do. They might not actually realize that this is a feature that's not included. They'll just assume that someone else had tested it. So these can often slip through, and we'll find that in actual fact they've introduced a vulnerability either in stability or in security into the system. So they really do need to be managed. The developed but not tested, this results from a disconnect between that product baseline final and the functional baseline. So the functional baseline is what is defined by the systems engineer through the design process and saying, this is what's going to be delivered in this build. In a single build development, that means it's everything. But most things that are fairly complex will actually do staged development. Therefore, you will only actually develop certain capabilities for each phase of development. These capabilities that you are developing for each phase, you allocate. And these allocations go not just to the implementation team to know these are the things you must work on, they also go to the test team. So if they have incorrectly allocated, then obviously the test team will not have written tests. If there is not sufficient traceability, meaning the test team isn't making sure that they are writing tests specifically for the allocated requirements, then they will miss things. Also, if the verification tests themselves have not been developed with reference to the use cases for context, what you can often find is that the tests themselves on the face of it appear to be complete, but they've lost context. And the test actually isn't really testing the scenario that is being targeted for this capability. And therefore, it's not truly valid. So the use case reference for context is quite important. And this particularly applies to things like alternative and malicious flows within a use case, where you are looking for those security problems, or those behaviors under conditions of failure, or the non-sunny days, the edge cases. So if a test has been written, it might very well cover the sunny day, the 80% of the time I do this. But if they haven't used the use cases to identify, what about that other 20% when something doesn't work, or when we're doing something a little bit different than normal, or when we perhaps have to guard against a security vulnerability, then the test is not actually sufficient. The defined but not developed, this results from a disconnect between the operational baseline and the functional baseline. So this means, again, incomplete traceability between the baselines. We have not made sure that the sets of requirements that we defined at our operational baseline flowed through completely to the functional baseline. Incomplete system level use case development. So use cases should be employed at various levels of development. They certainly should be employed at the operational level to figure out what the operator needs to do. But there's also system level use cases that need to be developed to identify exactly what the system needs to do, what other systems it needs to interact with, and what are those edge cases we talked about from a system perspective versus an operational one. And if you don't do that, then you can end up with a discrepancy in this area. Also, you can have inconsistent validation test case development. So this is where the test cases just aren't written properly, often because they haven't incorporated use cases, or they have not paid sufficient attention to the traceability. Inspected but not defined. This one is very common because the customer comes in and they're not actually technically astute. That's why the rest of us have been hired, to actually address the technical needs. The problem is they come in and they don't actually know what to ask for. This is where operational use cases are critical. And this is a step which is often skipped over in the systems engineering process by many programs, including very large programs. So things like the Phoenix program here in Canada. The main failure of the Phoenix program, whenever you actually look through, they call it out as project management. There were certainly some project management failures, but the main failure was systems engineering. And one of the root causes was absolutely their inattention to use cases, operational use cases. They did not pay attention to the edge case scenarios of where somebody has gone on maternity leave, or somebody has been promoted into an acting role. So their responsibilities have changed, perhaps their pay has changed, but it's not actually a promotion, so you can't process the promotion through the system. All these sorts of edge cases, they missed them. And fundamentally, when they tried to implement it, they implemented it in a manner where it was difficult to add them in later. And that's because they did not spend time on the operational use cases. That's it for today. I hope that might be of some use to people. The ability to actually step through in a very methodical manner to manage this level of complexity is fundamentally systems engineering. Model-based systems engineering provides you with the specific tools to make sure that traceability from the beginning all the way through, not only to the tests themselves, but the test results. That is a powerful tool to make sure that we can identify where potential disconnects could occur prior to them actually occurring, and therefore avoid the mistakes that are so costly to fix after deployment. Thank you very much.